Hello and welcome everyone. In this day 32 learning, we are going to be starting out with sorting. So, there are many different algorithms in sortings. We will look at bubble sort, selection sort, and insertion sort in this session. All of these are of n square time complexity and uh, are kind of not so optimal sorting techniques, but an easiest ones to understand. So let's understand what sorting really means. Let's say we would be given with an array of numbers, right? So let's say we would be given with an array of numbers. So this is an unsorted array. Uh, in order, we can use multiple sorting techniques. So after sorting, we would write it something like an ascending order or descending order. This is ascending order starting out from small 40, 50, right? So this is how we sort the array. So there are few algorithms that uh, are there to do this work. So yeah, so but why we sort helps in faster search and specifically in database systems. Such algorithm is very useful either to sort ascending, descending, or to have faster search. So uh, such applications require optimal sorting with different kind of different kinds of needs. Let's say few requires minimum number of comparisons or minimum number of time complexity, or the swaps between two elements that happen in sorting might be needed as a lesser one, and another place might require more. So such things all depend. So let's understand classification of algorithms. Classification of sorting algorithms. So we can classify them by comparisons. Comparisons simply mean the number of operations that we take. For example, um, let's say we compare each element with all the other elements in the array, or let's say for example here, let's say in order to sort this one, we take this element and check with all of these, and then we place it like a bubble sort at the top, and similarly we consider this element. This is a typical bubble sort. We check it with all the other elements, and then uh, move it to the last element, ignoring that the last position was already completed. So similarly we take all of the elements, place them accordingly, right? So with each iteration we get bubbling of elements to the top. The topmost uh, value will be the heaviest, second one will be second heaviest, third heaviest, and so on till all the elements are sorted, right? So that's a typical bubble sort. So comparisons are nothing but the number of times we uh, check an element or swap between two elements. So that's one thing. So there might be other sorts of algorithms where there might be non-comparisons also. So consider bubble sort as comparison example. Non-comparison, uh, consider radix sort. I will just briefly give an idea of what radix sort means. So in radix sort, consider an example where let's say 3, 1, 5 and 1 and 23 and 3. So consider this as an array. So in radix sort, what happens is we we simply rearrange the elements based on the number of digits in each of the value. So first is a single digit, second is two digits or the one that have 10th digit in it, and a 3-digit number is placed third, and 131. So this might be another sorting algorithm as well. So next is number of swaps. So first we understood comparison as a first way of classifying our algorithms, the number of times a specific element is compared. Next will be number of swaps, and a number of swaps means, let's say, we would swap a specific element. Let's say in this bubble sort, let's say if 10 would have already been here, it would have been ideally not required to be swapped, or if 50 is here, it wouldn't have required to swap. So it is two less swaps, and these set of elements would have or would not have required to be swapped. So there are certain algorithms which require lesser swap. So we will look at how that happens as well, right? So that's one thing. And third thing is memory space. Memory space, like in simple terms, memory space we can simply understand based on the additional memory. Like for example, in swapping two values, we might require a third empty temporary placeholder. So this might be additional memory overhead. So yeah, just like space complexity, how we calculate, we also calculate memory of worst case space complexity and memory space. So think about it the same way as how we calculate space complexity, right? So and few algorithms would can be done by recursion or not. Like for example, bubble sort, insertion sort, selection sort, none of them will be can be devised by a recursion sort, recursion function. While let's say if we take an example of a quick sort, we can divide quick sort or merge sort. It can be recursive. Like a merge sort splits a large array of n items into smaller array and then individually merges them back to their positions, right? So there is a pattern that we can devise with recursive functions. So that's one thing. And next thing is stability of an algorithm. So to understand this, let's say we are given with an object. So students. So let's say Amit, age 20, uh, Nikhil, age 20, and Geet, aged 18, or was aged 15. So certain algorithms, while you see these two positions uh, should be moved to here, but the order of these two should still remain the same, while certain algorithms shuffles these positions as well. So that's where stability of an algorithm is also decided, right? So next thing is uh, adaptability. Like, for example, we were talking about swaps. So let's say a portion of an array is already sorted. The algorithm should be able to adapt such that it only sorts the unsorted portion of the array. So that's one way to understand adaptability, right? So yeah, these were few classifications of sorting algorithms. Another set, another way is internal sort. Int- uh, so there are few other classifications like internal sort or external sort. Internal sort simply means we can sort it within an array. Like we don't need any separate memory or additional space to transfer any portion of it. While there are external sorting algorithms which require some uh, bucket of bucket of memory, just like a swap operation, which requires a temporary storage to store some portion of an array, right? So these are few ways. So yeah, external and internal sort. Like you can also think, let's say, uh, radix sort will be an external sort, and then the radix sorted array can again be passed to another internal sorting algorithm or bubble sort, which might be much better optimized. Or if we directly pass it to bubble sort, it might be less optimal because uh, we are dealing with a entirely unsorted array, while radix sort might bring about certain elements sorted with the way that the digits are, right? So think about it that way when we uh, talk about internal and external sort, right? So that's about classifications of algorithms. Now I will quickly jump to bubble sort and let's start understanding it. Switching to a new page, let's talk about bubble sort. Let's say we consider an array 1, 2, 5, 3, 1, and 4. In order, we know that in order to sort this one, um, consider bubble means the elements floating to the top. So the way that bubble sort works in simple terms is we start out here and we compare this element with the adjacent one, and we swap if uh, this is a larger element. We consider this as a larger element, and we compare this again to this one. Since this is not larger than the previous selected element, we continue uh, comparing with all the other elements. If uh, once we reach the end of the array, then we move the largest element to the last position. In the first pass, we could have something like this. Let's say 2, 3. 1, 4, and 5. This would be the sorted portion. Similarly, in second pass, we check these two. 3 is the largest one, so again we compare 3 with 1. 3 is still the largest, and 3 with 4, 4 is the largest, so we leave it as it is, right? So then we say these uh, this is still the start. In the third pass, we compare 2 with 3. 3 is the largest value, and 3 with 1. 1 is the smallest one, so we push 3 to the end with this way. So I hope you understand the whole idea. So the way that this gets devised is, we start out with for loop I starting from 0 to n, length of the array, and similarly j starting from 0 to n minus I. So we only iterate, uh, let's say we are at 0th step, we only iterate till the end of the array. Let's say we are at second step, we already know that the last position will already be sorted, so we decrease our end pointer with j, right? So that's the whole idea. So with this, we check if a of j is array of j is greater than array of I, array of j plus 1, sorry. So if the next element is greater, then we swap array of j with array of j plus 1. So we do that, and once at the end we return an array. So yeah, this is a simple bubble sort. Yeah, let's look at one more example of an array. Before even jumping to JS bin, where I quickly show the code for this, I will even talk about another array example. Let's say consider um, an example where we would have an input of 2, 1, 3, 4, 5, right? So we know that this portion of the array is already sorted. So what would be a better optimal approach in order to minimize the number of swaps or the operations in bubble sort would be, let's say we can add a pointer called, we can add a flag called swap, saying swap. Here we can introduce a pointer called swap, initially set it to false, and if swap false, we swap say true, and after the for loop, if there are no swaps, like let's say we will understand, we will walk through this algorithm with this example, maybe just a second. If swap is still false, then already sorted. So let's understand what we mean by setting swap to false and swap to true, and again knowing that the array is already sorted. So what I really mean is, let's say in the first iteration we know that we need to find the first largest element. So 2 compared to 1, 2 is larger. 2 compared to 3, 3 is larger. So we still keep 3. 3 compared to 4, 4 is larger, and 4 compared to 5, 5 is larger. So we would have only swapped uh, 1 and 2, right? So which means we would have ended up with 2, and we would have left all these other elements unswapped. So in the second iteration, we start out with this pointer, and we would not be having um, any more swaps, which means, let's say we start out from, as per our loop here, so we start out from 0, 1, so we start out from 0. So let's, I will quickly erase all of my drawing here. Try re-explaining this. So 2, 1, 3, 4, 5. So with this, in the first pass, we check 2 is the largest value, and since 2 is is greater than 1, so we leave it as it is. Since next would be um, 2 we see greater than less than 3, so we swap it, like we have a condition here. And we swap these two. Once these two are swapped, which gets 1, 2, 3, 4, 5. Since 2 is greater than 1, we swap these two in first iteration. And in second pass, we take this, we start out here, and we check if this value is less than any of these, which shows none. So our swap value or swap pointer still says false, indicating that we have already sorted the array. So that's the whole idea here. Let me quickly jump to the JS bin and quickly show how this code is being implemented, right? So yeah, so here at JS bin, I've already run this simple example. Just a second. Okay, so in this JS bin, I have firstly added the bubble sort algorithm, which is optimized as well. So as you see, we have a swap pointer here, and yeah, we are swapping values this way if the element, previous element, or is greater than the upcoming element, then we swap it to bubble it up. So yeah, that's the whole idea. So after third pointer here, we would not be having to find any more swaps, or the swap pointer stays at false, uh, which means we already have a sorted array, right? Hope you got that idea. I will quickly move to the next algorithm, which is selection sort. Starting out in a new page with selection sort. So this is the second sorting algorithm, and yeah. So we also should know that bubble sort. Let me switch to JSPin. So bubble sort will always have a time complexity of O of n square, as worst case time complexity, and if it's already sorted we would have O of n, and space complexity is O of n square in the worst case. Yeah, the optimized one is slightly adaptable. Yeah, see the swaps to be similar to space complexity because we have two for loops here, right? Okay, so that's about it. Let's go to selection sort. I will quickly explain the idea of how selection sort works, and let's then come back to the JS bin. While we have already understood the bubble sort simply pushes the largest element to the top, and as iterations passes by we get the refined or the sorted array with top of the last element of the array being the largest one, and slowly having to form the sorted structure. Similarly, in selection start, we end up with we sort the array by selecting the minimum value and then having to swap it with the related position, and we start out from the beginning of the array. Let's say we have an array, let's say an array of 5 3 8 4 2. So we start out with min index 0, min index, and we start comparing this element is greater than any of the other elements. So after the first pass we get a min index value of, let's say, 0 1 2 3 4, right? So min index will be 4, and we swap it with the fourth index with the pointer I. So and j pointer starts going this way, right? In second pointer swap with I pointer. So that's about the logic. In second, while in second position we end up with something like this, and min index will be 3, which is I itself. So we swap, we do not swap as I if I and min index are the same. We can even ignore, or but we can still swap or still ignore it, right? So that's about third pass, second pass. So in the third pass we would be having our I here, and we know that 2 and 3 will always be, we will already be uh, here. So we take this one in the third pass and we check if 8 is greater than 4. Yes, so we have min index here, and our min index will be 3, and we swap it with I, which is at 2. So yeah, so that gives us 2 3 4 8 5. Similarly, these two swap in the fourth iteration. So yeah, that's the way that selection sort works, where we would be having a min index. So the way that the algorithm would be defined would be again a two for loops, I starting from 0 to n, length of the array, and a min index at each iteration set to I, and a j pointer which starts from I plus 1 to n, and check if a of I is greater than a of j. right? A of min index, sorry, a of min index is greater than j. Then assign new min index, and finally add with this j loop ending if index is not equal to I, swap, right? Swap the value at min index, and the swap the value at. So that's the whole algorithm logic. So let's quickly switch to JSPin and let's quickly look at the code for this one. Yeah, so let's say we start out at 0, n minus 1, and we say I plus 1, and then we reassign the min index to a new value, which is the second for loop pointer, and then we swap at the end of this iteration of the second for loop. Yeah. So similar to bubble sort, but bubble sort bubbles the largest value up the chain. Selection sort uh, always presents us with the lowest value at the start of the chain. So yeah, let's go to insertion sort, and time and space complexity for this one. It's similar to bubble sort, where worst case is always n square. Uh, same with uh, same with the space complexity. It would be of n square. Yeah. Let's go to selection sort, insertion sort. So this would be our last algorithm. I'll switch to drawing board again, maybe even have a new page started. The last sorting algorithm for today's session. So selection sort. So the way that selection sort can be thought about is, let's say we are playing a deck of cards. We would sort, let's say we uh, take a pack of cards, we continuously arrange them in sorted order, like placing a card into right position in the in the to the left of it in a sorted way. uh, like we consider left portion sorted, sorted, and any new element are placed accordingly. The sorted left portion, already sorted left portion, left portion. So this the whole idea. So while in case of an insertion sort, so sorry. So this should be insertion sort. Excuse me for the wording mistake. So yeah, that's about insertion sort, where we consider a left portion of an array to be sorted, and any new elements coming in will be placed in a right sorted order of the left portion. That's the whole idea. Like Let's say we take in an example of 53842. So in case of insertion sort, I'll write insertion sort here. So we consider first pass to be case of selection sort. We would already be sorting 5 with 3, 8, 3. So in case of this one, it stays the same way, and in case of second pass, we move our I pointer here and we swap these two, 3, 5, 8, 2. In case of selection sort, we continue from this pointer and we assume this as the min index, and we see if we swap these two, 2, 3, 8, 5. In case of third pass, we will not be doing anything here, 3, 5, 8, 2. And in case of this one, we swap these two values, 2, 3, 5, 8. So in the last case, we push this to the starting of the array or position. So in each case, we consider this as sorted array, this as sorted array, or this as sorted array. So that's the whole idea. 5, 8. So that's the way. Finally, here we would run out of iterations and we would let it go. So in case of insertion sort, the way that algorithm works would be, so we start out with an array 0 to n, 0 to n, and we also would have a key a of I, and while loop to sort the elements in the left portion of the array, like a of I, let's say here we also consider I minus 1, I minus 1. So we consider if j is greater than key, then we swap, and also we constantly check if j is greater than or equal to 0. So these are the two conditions to sort the left portion of the array, right? So we swap the I j pointer j plus 1 with a of j. So that makes sure the left portion of the array is always sorted if it's greater than interchange swap. And we constantly sort the left portion of array this way, right? So after this, then we move the equals to key. So yeah, this is the whole idea. Let me quickly switch to JSBin and let's quickly understand how insertion sort algorithm works. So like I said, we continuously iterate through the array, selecting a key value or a specific I pointer and the specific element, and we constantly arrange our left portion of the array, right? With a while loop which says which considers the index I and everything behind it to the left portion of it, and we swap the elements if a specific value is less than the previous value. So this is the whole logic. Hope you were able to understand insertion sort and selection sort. Please do take a look at many different examples and have a good understanding on this one. If you have any doubts or clarifications with my explanation or anything around insertion sort, bubble sort, or selection sort, please do post them in the comment section. We'll be happy to read comments and interact more. In the next section, we will be looking at merge sort and quick sort. Those would be an optimized algorithms in sorting techniques. So those will be set of optimized algorithms which run on O of n log n time complexity, while all of these that we had here will always have O of n square time complexity. Hope you found this video helpful. Please do like and subscribe to my channel. Thank you.